talk more about the final. So not very many people here, so I'll probably have to keep admitting participants as we go. But so you should be able to, you should, right now, do you see my screen, or do you see the PowerPoint? Right, you should.
The PowerPoint.
Yeah, that's right. Okay, good, thank you. Okay, so let's go ahead and get started with this. So hopefully the exam wasn't too painful. We'll go over that when I get back. It was meant to cover the material that we talked about. There were a couple of curveballs in there that I wanted to see how you guys thought. So I'll adjust accordingly if those didn't work out. But the only thing really we have left to discuss is the chapter 17, which is really just looking at stuff that you guys have already done and just applying it to rigid bodies. And so the two things that we haven't done yet are energy and momentum. Those are the two. And so once those have started, then once those have been covered, then pretty much we've done everything we are in the class. All right. So first thing, this is where we are with it. We have, as you know, we talked about with rigid bodies, we did force and acceleration. That's what we spent most of the time we were before the exam. That was chapter 16. And then the last thing, this is essentially 17.1 is work energy. And then 17.2 is impulse momentum. Now, there's not a lot of theory to go over because nothing's really changed. And so you're really just going to apply the stuff that you already know and to the new problems that we're doing. All right. So that's our impulse momentum. So the one big change, and let's just go through the work and energy. Now, this stuff has a lot of information on it, but let me point out the important stuff. So we remember this equation here, T1 plus U1 to 2 equals T2. So that's just saying that we have our initial state. It could be an initial velocity, it could be an initial position, it could be an initial MGH. Remember that whenever we're dealing with energy, we have all the energy that we start with on one side of the equation, and then we add to that the change, and then that equals the final. And so that's, we went over that ad nauseum in particles. And so when we're dealing with rigid bodies, the only difference is we have to account for rotation now, which we didn't have to do with particles. Now, when we're dealing with a rigid body, you recall that whenever you talked about U1 to 2 dealing with force displacement. So for example, if you had a particle, probably better, let me do this. So if you have, remember that if you had a particle and is moving in that direction, then, and this was our T1 here, then our plus U1 to 2, that could just be then equated to force times distance. And then that would all equal our T2. So we had some simple examples where we'd have, say, a car moving at, say, 10 meters per second. So it had an initial kinetic energy, and then we'd apply some force over distance. And then that would then allow us, to find its final, right? Because that's a simple example, but we have kinetic energy in joules, force times distance is also joules, and we get our final answer in joules. So the difference with rigid bodies was what that slide was talking about, was that if you have a force times distance, what if you have a rotation? So let's say you have something that can rotate. And so if you apply, say, here's our starting point here, and we apply a force, and that's our distance r, so that becomes a moment. So moment equals F times R. then if we want to know the work that that moment does, it's just going to be how many rotations does it make. So that's our distance. So it becomes u1 to 2 is now equal to moment times theta. So this is analogous, right, to force times distance. It's just moment times rotation. So we can use this to solve problems if we were told, for example, that a moment of so many Newton meters was applied over so many revolutions. Then we know that, say, for example, if we had 10 Newton meters and we applied it over so many revolutions, well, if it's one revolution, that would be 2 pi. And then that allows us to get a answer in terms of joules. So that's how much energy was put in, okay? So that's what that's referring to, this m times theta. That's the only thing that's really new in energy for this section. Any questions? Okay. Let's go back to the, so that was what this equation was down here at the bottom. So m d theta becomes m theta 2 minus theta 1, or basically the distance that theta moved. That's if m is constant. And we won't deal with things where m isn't constant. But you can see how we're taking the very simple values or the simple applications of all these things. And you can see how the complexity could get very big very quickly. Okay, so the other part we have to deal with is also the fact that because we also have rotation, we have to deal with the energy of rotation. And so this is the derivation that shows where we get that from, but you'll recall that anytime you're moving the center of gravity of a rigid body, that's going to be 1/2 mv bar squared, where v bar is the mass, is the velocity of the center of mass. And then you have to add to that the sum of all these little m1 v1 squared. And so it turns out, though, that if you break those out, the m1 v1 squared, you end up with, and what this is saying is that if you have other velocities in your particle that you have to deal with, you have to add those to the central or the velocity that's due to the motion of the center of gravity. But the important thing to take away is that that essentially reduces to this relationship here, which we recognize r squared m as our moment of inertia. And so what we have now is we have the kinetic energy of the motion of the object moving in a straight line plus its rotation. And so those are considered separate animals, so to speak. So if I were to, let's see, if I were to do this again. So if we were to say, for example, that we have our blob and it's moving through space, but if it's also rotating, then it's not enough. The energy has to be described by the rotation. So energy equals the translation plus the rotation, right? And so as a result, you have the 1/2 mv bar squared, and that's just due to the center of mass moving, plus the 1/2 I bar omega squared, where again, that's the center, or I'm sorry, the moment of inertia of the mass moment of inertia of the actual particle about its center of gravity, and then its respective omega. All right. And that's and those are only two terms that are new with rigid bodies: the moment that you have to take into account for its motion, and the addition of this I omega squared term. That's it. And that's what's summarized here. Okay. Any questions on any of this so far? So the new homework is posted. It's not due until late next week. So I imagine you may have questions on that between now and then. Now here's a conceptual question. So if we were to take three objects, but both have this, they're both round in a sense. I mean, one's a sphere, one's a cylinder, one's a hoop, and we were to put them on this incline and let them fall down and roll down the incline. The question is, which one will travel the greatest distance x? And so we have a solid sphere, and so the solid sphere has a moment of inertia of 2/5 mr squared. So all right, this 2/5 mr squared, that's for the solid sphere. And then the solid cylinder is 1/2 mr squared. All right, so that again, the solid sphere is 2/5 mr squared. The solid cylinder is 1/2 mr squared. And the hoop is just mr squared. So knowing the difference between the three, which one would you predict is the one that's going to go the farthest? So remember that the moment of inertia is the value that's going to resist rotation. So it's the equivalent of, or the analog of mass in F equals ma. So which one has the greatest rotational mass? That's going to be the hoop. And then the next one is going to be the cylinder, and the next one's going to be the sphere. So the sphere has the least rotational mass, and I say that in quotes because it's not really mass, it's the rotational moment of inertia. So because the sphere only has 2/5 mr squared, that's the one that's going to be the least. Okay. Sorry, it might be much easier to have a board, but does that make sense? Any questions on that? Okay, good. And then the second, excuse me. The second one has a steel sphere, radius r, mass m is released, and then if you were to take the equivalent sphere that had two times the radius but the same incline, what will its speed be after rolling a distance d? So on this example, you have both a sphere with radius r and a sphere with radius 2r. And so in this case, the answer is going to be just v, because they both have the same moment of inertia, and the radius has no bearing on the actual final distance that it's going to go. And so, or I'm sorry, on the velocity, since they both have the same moment of inertia and they have the same mass. So this one's a little trickier, but that's the for the final, there will be a few conceptual questions, and they're not meant to be tricky, but you'll want to think about them. And I haven't really talked about the final much yet, but the final will entail 4 to 6 questions, and one of the questions will be conceptual, where you'll break up the concept. You'll have 6 questions per se, and those will all be short answer conceptuals as opposed to long calculations. So I would go back and just make sure you understand what's going on with this stuff, because that will help you in that part of the test. And we'll talk about this more next week. Okay, let's do an example now. So this is an example now that we only have, as I said, we only have a couple of new concepts. And so I printed, or I posted the sheet for this on Canvas, so you should have this problem. So in this case, we're looking at a object where we have a spring that's stretched. All right. And so I'm going to go ahead and write down so we know it's 12 kilograms, 30 grams, 2 meters, looks good. All right, so I'm gonna. All right, so here's our example here. All right, so in this case, what we have is we have our spring that is stretched, and here is our endpoint, and we have a 2-meter, 12-kilogram rod. So our rod is 2 meters and 12 kilograms. Okay, and so one of the first things we're probably going to want to figure out is what is the moment of inertia of this. So let's think about how this problem is going to work. So our rotation point's up here. All right, this thing is going to sweep a curve like that as it relaxes, and we're told it's initially at 30 degrees, and then we want to find omega when spring is relaxed. All right. So it makes sense that if we want to know omega when the spring is relaxed, we're going to need to know what the how far the spring is stretched initially, so that we can then compare the initial and final conditions. And we're also going to want to know where this bar is initially and final, because it's going to have a change in height, an MGH associated with it. Okay, so we're going to use our equation T1 plus U1 to 2 equals T2. But there's a couple of things we can figure out before we start. For one is, this is how the spring is, this is how far it's stretched right now. Now we're told that the spring, when it's relaxed, it's 2 meters. That's the writing in the problem. So, but how long is this right here? Well, if you first look at it, you say, well, how am I going to tell that? Well, this is, you can use the law of cosines, right? Because you know that's 30 degrees. So that has to be what, 150, right? So if we use the law of cosines, we know 2 included 2. So we can calculate this total length here. If we do that, this ends up being, and we'll call this length, equals 3.864 meters. All right, and so that'll be the length of that. And we'll just call that length BC. All right, so length BC is 3.864 meters, so we know that. So we know essentially when it starts, if it's 2 meters when it's relaxed, that means it's been stretched 1.864 meters. So its X distance, X initial, is 1.864 meters. All right, so far so good. So we're just finding out some preliminary things, then we'll put everything together. The other thing is, we have a 12-kilogram object, and so it's going to have a certain MGH. So we want to think about what's its Y initial, what's its Y final. Well, when the spring's relaxed, this is going to be 2 meters. Well, we know that this is 2 meters. So the only way that that's going to be 2 meters and that is 2 meters is if this is a equilateral triangle. Therefore, that's going to have to be 60 degrees. All right. This is 30 degrees over here. So since this is the middle, we know that if this is 1 meter, then the opposite side of a 30-degree triangle is 0.5. So we know that Y1 has to be 0.5. If we look at Y2, that's going to be the opposite side of a 60 degrees. And so that's going to be root 3 over 2, or Y2 is 0.866 meters. Okay. So I have that so far. So the other thing I need to know is, what is the moment of inertia? All right. So the moment of inertia is, again, since it's a slender rod, it's going to be 1/12 ml squared So I is equal to 1/12 ml squared. And then I have to add to it plus its md squared because we need the parallel axis theorem since we're rotating about this point here, point A. So if we calculate that, that becomes 1/12 times 12 times 2 squared plus 12 times 1 squared. And so that's essentially 4 plus 12. So that gives me 16 kilogram meter squared. All right. Okay,
Wait,
so
Professor,
yes,
so why do you take it about its point of rotation? Or it makes sense why, but like I'm just a little confused by that part.
you mean why do you take it about its point of rotation?
Or like the parallel axis theorem part.
Oh, well, because whenever you're doing, so if you think about rotation, if we say, for example, if this was my slender rod here, then the 1/12 ml squared is based on rotation about the center, right? Just like if you think back to statics, if I said here is a rectangle, and this would be 1/12 bh cubed, right? And that was the moment of inertia, right? But if I took it from somewhere else, like down here, then I'd have to do plus 80 squared, because you always take this equation for the object is based on its centroid, but you're not always rotating about the centroid.
So it just represents the moment of inertia about the point.
About the point, yeah. So it could have been anywhere. So in this case with this one, if it could have been, I mean, if this had been longer, well, I guess it wouldn't have been made practical sense to be longer, but I mean, I could have taken the moment of inertia about up here and that would just made my 80 squared longer. But the basic equation you have to use is always about the centroid. So it's always the mass moment of inertia about the centroid plus the md squared term, always. Okay. All right, good question. So, so now we can continue. And so if we look at, like I said, as we have our delta y here, so really the distance this falls is delta y, which is 0.366. So we could leave this, we could make this our datum, this point here, and then we only have to worry about that. Okay. So if we set up our value, then what do we have? We have T1. So let's go with T1. So we have no initial velocity, no initial omega. So say T1, that's 0. Okay. Then we have plus V1 gravity. All right. But we're making this initial point our 0. So we're going to say that's 0 also. And then we have our plus V1 elastic, right? And that's for our spring. Well, we do have that because we know that our spring is stretched at 1.864. So we know that's going to be what? It's going to be 1/2. So we'll just go ahead and put that. So 0 plus 0 plus 1/2, 40 newtons per meter times 1.864 meters squared. Okay. So there's my elastic energy. All right. And then I need to know what is the speed on the other side. So that's going to equal T2. So T2 is going to definitely have velocity because we want to know how fast it's going when it's going around the corner, or I mean, when it's at the point where it's relaxed. And we also have V1 gravity. And we also have, but at this point, we have no elastic energy. So V1 elastic is 0. Okay. So we're going to then add this. And so what we'll end up with is we're going to subtract off. This is going to be actually subtracted from the other side because it's going to be added to this side. So this will be equal to, now the T2 is going to be 1/2 16 times omega squared. Okay. And that's just 1/2 I omega squared, and I is this. So that's what my T2 is. And then the only other thing I have is my energy, which is going to be, in this case, it's going to be minus 12 times 9.8 times the net distance, which was 0.366. Sorry, squished in there. All right. And there we have it. So the way to think of this is I've subtracted it over here. I could have put it over here because really what this is doing is we don't want to add it to this side because that's going to detract from the omega, and the omega is going to be faster because it's falling. So this energy really belongs on the other side, or it can be subtracted from this side. Either way it works. So at that point, we have everything but omega. And so now we can solve, and we end up with an omega equal to 3.75 radians per second. All right. So you notice that this is very similar to the stuff we've done in the past. It's just that we only have rotation in this case around the point. And so if we had something that was actually not fixed to a fixed point and was actually moving, then we would also have to add in the 1/2 mv squared. So we'll deal with that in other examples. But so hopefully that makes sense. Any questions on this problem? Okay, good. All right. Look at is this next one here. So this one's a little more involved. This will probably take us the next 20 minutes to bust through it, but we can finish it. Okay, so here we have a uniform cylinder, 4 kilogram cylinder A. It has a radius of 1.15, and it has an initial angular velocity of 50 radians per second. So imagine A is rotating, and then it slides against the identical cylinder B, which is at rest. So of course, initially the two are there's going to be sliding, and which we call slipping, or slipping and sliding, whatever you want to say. And then they will attain a constant angular velocity that's equal, because it has to be if it's not slipping anymore. And then only in opposite directions, which follows because of the way they're rotating. And so we're given that the amount of rotation before they achieve that is 3 revolutions for A and only 1 revolution for B. So when you're reading this question, it might seem very esoteric, but when you pick out the little pieces of it, for example, you see it says cylinder A executes 3 revolutions. Well, you remember that what is the only force that's going on A and B is friction. So friction is actually going to apply a moment, friction times the radius, and it's going to apply a moment over 3 revolutions. So that gives you an idea of where that energy is coming from, right? So you have 6 pi essentially for A times the moment created by the friction. So again, this is an energy problem. It's just a matter of keeping track of all the energy that's going on. All right, so I went ahead and drew this out ahead of time, but here we have, so we have the mass today is 4 kilograms. You have mu k is between the two, B is at rest, omega naught's 50 radians per second, R is 0.15, and we want to find what that friction coefficient is, and we want to find what the final omega is. So again, we're going to use our T1 plus U1 to 2 equals T2. And so we know that A spins and slips. A has 3 rotations before reaching constant omega. B requires 1 rotation before reaching constant omega. So if we go ahead and we look at the free body diagram for it, it looks essentially like this. You have, and I should have put weight here too. There's weight. And so you have friction, normal force, friction, and then you have the reaction A, because the thing's being, as this pushes this way, it's going to push the cylinder to the right, the reaction is going to be the left. Now it's good to recognize these and put them in your free body, but it turns out that we're not going to use any of these values in this example, because we're going to end up taking moments about the center point, in which case everything's going to disappear except the friction force. One thing too, I cylinder is 1/2 mr squared, so I went ahead and calculated that. So we know our I is 0.045. All right, so we have all the information we need to start the problem. So one thing we're going to look at first is if we sum the forces in the y to 0 on this, then we'll know, and this is stuff you almost do intuitively, n minus w equals 0. Therefore, we can calculate what our normal force is, right? And so this is, again, this is for cylinder A we're dealing with now. So for cylinder A, n is just going to equal 4 kilograms times 9.81, which is 39.2 newtons. All right. Therefore, we know, since it's slipping, that the friction force is just going to be equal to mu k times 39.2. All right. So we'll need that for later. The other thing we want to look at, what is the initial kinetic energy? So initial kinetic energy, T1, that's going to equal 1/2, because we're just dealing with rotation, I omega naught squared. So if we plug in that, we get 1/2, 0.045, and then 50 rads per second squared. And that gives me 56.25 Newton meters. Okay. So that's just the kinetic energy that the system has to start, because the only kinetic energy is that of the rotating cylinder. Then I want to look at what is T2. So T2 is going to be essentially the same thing, except I don't know what omega final is. So it's going to just equal 1/2 0.045 times omega final squared. Or I can write that as 0.0225 omega final squared. And I'm just writing that out, what it would look like based on just carrying through the 1/2. All right. So now the last thing I want to look at is what is the moment created about A? Because remember, I said again is that the only force that's here is the friction force, and is creating a moment about this for 3 full rotations. So with that, we're going to say the sum of the moments about A equals the friction force times R, which we can write that as the moment about A equals mu k times 39.2, because that's my friction force, times the radius of 0.15. So this gives me a value of 5.88 mu k. All right. Now, remember that the mu 1 to 2 was equal to m a theta a. And the reason I'm putting a negative sign in is because that's going to take away kinetic energy, isn't it? It's not going to add kinetic, it's actually subtracting. So I'm going to have that as my, if I put in my moment, that's going to be 5.88 mu k, and then times theta a. Well, it takes three revolutions that's occurring before friction stops occurring. So that's going to be 6 pi. Or that's going to give me a number of negative 110.8 mu k Newton meters. All right. So far, so good, I hope. All right. So now what we end up with is we'll say this is our, for cylinder A, we have our T1, which was 56.25. So 56.25. Actually, let me write that a little. T1 plus U1 to 2 equals T2. And so our overall equation then is 56.25 and then minus 110.8 mu k, and that equals 0.225. Actually, there's a 0 in there. Omega final squared. Okay. Now it turns out that omega final, omega A final equals omega B final. I think we can agree with that because after 3 rotation, it tells you that it's going to be rotating and not slipping. So we know that those two have to be the same. So we can, instead of saying omega A final, we can just put omega final here, and that's going to be consistent for both cylinders. So this becomes one equation here. All right. And we have 2 unknowns, so we have to then now look at cylinder B. But before I go on, are there any questions? Does this make sense, the whole process? Because this is an important example because it encompasses rotation and it also encompasses the moment. And so I just want to make sure you guys are following everything. All right, that's good. All right, so we have everything. So there's our equation. All right, so now we need to move on to cylinder B. So for cylinder B, we know that T1 equals 0 because we're told that initially that cylinder's at rest. And we know that T2 is going to be the same thing. It's going to be 0.0225 omega final squared. And so now it's a question of what do we have for our energy, right? Or what is happening with our MB theta B? Well, we know that we can write it similar because the friction force, if we look back at this diagram here, the friction force times R is going to be the same for this as it is going to be for this. The only difference is this is going to be a positive because this is going to start at 0. You're going to have a moment created by the friction force times the radius, and that's going to be applied over 1 full rotation, and then you're going to get to your T2. So what you'll end up with in this case is you'll have your U1 to 2 is going to give you a value of, excuse me, is going to give you the same thing. It's going to be 36. No, it's not going to be 36. It's going to be, I'm sorry. It's going to be 5.88 mu k, right? Because that's the moment. And then that's going to be multiplied by 2 pi. So that total value then is going to give me a value of, yeah, that's right. Sorry about that. 36.98. So that's right. This is going to be 36.98 mu k. All right, so now I have it. So now what I can do is I can set it up. And I can set up for cylinder B. I have my T1 plus U1 to 2 equals T2. Now I have 0, and then that's going to be plus 36.98 mu k, and that all equals 0.0225 omega final squared. Or I can write this as 0.225 omega final squared minus 36.98 mu k equals 0. So if I take this equation and then I take my other equation, the one that we started at the top, and that was my 56.25 and minus 110.8 mu k, and then 0.225 omega final squared. So that's my equation 1. This is my equation 2. Sorry, it's getting kind of squishy. But so what I did is I took, this is the equation from cylinder A. So this is cylinder A. Sorry, it's a little messy, but it's 0.225 omega final squared minus 110.8 mu k equals 56.25. And then we have this one here. So we can easily solve because we can just subtract and get rid of it. And then we can basically solve for both of them. So that's just algebra at that point. So what we end up with then is when we solve this, we end up with mu k equals 0.380, or essentially 0.38. So friction coefficients aren't really good past 2 digits. You can't really know them to 3 unless you're in a really very controlled lab environment. So really to report it to the hundredths place is kind of silly. I'm sorry, to the thousandths place. And then our omega A, which equals omega B in terms of not direction, but magnitude, that was 25 radians per second. All right. So you notice with both of those examples, we used the I omega squared term, but the overall setup in that was still very similar to what we've done with particles. We still have the T1, U1 to 2, and T2. We just have to keep track of everything. And so hopefully you'll find that energy with rigid bodies is similar to what it was with particles. It's not meant to be super difficult. And I'm not trivializing it, but I think as far as the conceptually, I think it's probably one of the easier things to understand that we're doing. Any questions on this? All right. So the last problem that we were going to do is this one here, and we don't have time to do it today. I want to do it on Friday because that one's another good example. But this has several moving parts to it too. And the reason I want to make sure we do it is because this problem has both MVA squared and I omega squared in it. So it's a good a problem that covers everything. But if we just look at the basis of it, we have a double pulley and we have this 15 kilogram mass that's being slid up an incline. And so we're given the kinetic coefficient of friction. And then we have the cylinder block A that is falling. And so we know the system is at rest in the position shown, and then they apply a 200 Newton force. So we know our initial positions, everything's 0. And then we want to determine what is the velocity of cylinder A as it strikes the ground. And so there's going to be a certain velocity it's going to strike the ground at. But if you picture the inclined 15 kilogram object, that's not going to stop just because the 5 kilogram hits the ground. So if you picture it, it's going to have a certain inertia to it. It's going to be sliding up the hill at a certain velocity. Then that 5 kilograms is going to hit, and then it's going to keep going, isn't it? And so in a sense, the wheel will stop rotating, and that cord will then become loosely bunched, but that 15 kilograms will continue to slide. And so the total distance is not just, you'd be deceiving to say the total distance is 1 meter, because that's as far as 5 kilograms can go, but that's not true. So what we have to figure out is, what is the velocity of block B when block A hits the ground? So how fast is it going? Because then if you know its velocity, then it's just, again, an energy balance. You have 1/2 mv squared. It's going up an incline, so you have to subtract off its mgh, and you have to subtract off its force times distance due to friction. Hopefully that makes sense. I know it's hard when I'm just visually talking without seeing it on the board, but so I would think about that problem. We're going to go through it on Friday, but I want to also talk about momentum. We will end up lecturing on next Wednesday about momentum a little bit, but I want to make sure you have everything you need to do the homework by Friday. Okay, so we'll probably go through this problem, and then we'll talk about momentum, and then we'll wrap things up next week. So if you have questions, see me in office hour, but otherwise, you guys have a good rest of your day, and I will see you on Friday.
Thank you.
Thank you, Professor.
Thanks, you guys. We'll see you soon.